Okay, let's take a look at ethanol metabolism as it is going on in the liver in either both the fed and fasting states. So the metabolism of ethanol, remember, is just a series of a couple of enzymes-mediated steps, very straightforward. But the effects on the fed and fasting states can be very profound. So let's start in the fed state in the liver. In the fed state in the liver, we have GLUT2 activity because we are in an insulin anabolic state. GLUT2, of course, is allowing for the transport of glucose in the fed state into the cell. The glucose, of course, is being oxidized by glycolysis into pyruvate. One of the key steps in the glucose oxidation pathway is mediated by the glyceraldehyde 3-phosphate dehydrogenase enzyme. And this is one of our steps that's going to be generating NADH for energy production. Now, in parallel, if during a fed state we are consuming ethanol, alcohol also, the ethanol in parallel in the cytoplasm will be converted by alcohol dehydrogenase enzyme, which is going to convert the ethanol into acetaldehyde. This, of course, is going to be generating NADH. So we are contributing to the NADH levels inside the cytoplasm, contributing as is glycolysis. Now the acetaldehyde at this point will be transferred into the mitochondria, where it will be oxidized by acetaldehyde dehydrogenase. I'll abbreviate this ADH, and it will be formed into acetate. Being a dehydrogenase step, of course, this is going to contribute to the NADH levels in the mitochondria in a fed state. Now, the NADH that is generated in the fed state in the liver and the mitochondria, recall these reducing equivalents need to be transferred into the mitochondria to be put into the electron transport chain. The normal process in the fed state is for transferring these molecules by reducing DHAP into glycerol 3-phosphate by the dehydrogenase enzyme, and then of course the reverse reaction where we are going to take with the same enzyme and reduce FAD to FADH2, and then these electrons can be placed into the electron transport chain at the level of CoQ. Now, under normal fed conditions, this synthesis, this transfer of electrons in this electron shuttle mechanism is very efficient. But now let's add another complexity by adding more NADH generated from ethanol metabolism. What that is going to essentially do is substantially increase the concentration of NADH in the cytoplasm, because this system is getting backed up. The extra level of complexity here is added by the additional NADH that is being contributed in the mitochondria by the oxidation of acetaldehyde to acetate. This is going to dramatically increase the NADH levels in the mitochondria. Recall in the mitochondria, these are going into the electron transport chain. And so the electron transport chain will become essentially saturated. So the concentration of NADH, both in the matrix of the mitochondria and in the cytoplasm, will begin to increase. With elevated levels of NADH in the cytoplasm, we stand to face a potential inhibition of glycolysis because of increased NADH levels, lack of NAD for the glyceraldehyde 3-phosphate dehydrogenase reaction. So therefore, what we were going to do is shift the pyruvate, instead of entering the mitochondria to enter the TCA cycle through acetyl-CoA, the pyruvate will be converted into lactate. In doing so, we will be able to regenerate some NAD in order to keep this reaction going. Now, under extreme conditions, the lactate can enter the blood and cause lactate elevation, concentration in the blood. Because this is an acid, it's going to cause lactic acidosis. Essentially decreasing the pH of the blood. Now the next problem with ethanol consumption and metabolism in a fed state in the liver is over in the mitochondrial matrix. We have substantial amounts of NADH in the mitochondrial matrix, and that is going to inhibit the dehydrogenase enzymes in the TCA cycle. So acetyl-CoA and oxaloacetate will condense to form citrate, and then the next reaction to form isocitrate. But then recall the isocitrate dehydrogenase enzyme will be inhibited by high levels of NADH. This will cause the aconitase enzyme to reverse, building up citrate. Now under these conditions, the citrate will be placed out into the cytoplasm, where the citrate will now, by citrate lyase, be returned to its original state in the mitochondria as acetyl-CoA and oxaloacetate. Now at this point, the acetyl-CoA is going to be converted into malonyl-CoA. Recall this enzyme is the acetyl-CoA carboxylase. This enzyme is activated by insulin signaling. We are in a fed state in the liver, so we have subject to insulin signaling. The malonyl-CoA, of course, will be used to make fatty acids. The fatty acids, of course, will be combined into triglyceride structures. Now recall, we need a backbone for triglyceride, and that backbone is going to be the glycerol 3-phosphate molecule. We have excess glycerol 3-phosphate. We have excess because we have high levels of NADH in the cytoplasm generated from glyceraldehyde 3-phosphate and the oxidation of alcohol by alcohol dehydrogenase. And if we have inhibition of the electron transport chain, or slowing of it, because we have substantial amounts of NADH in the mitochondria, then our conversion of DHAP to glycerol 3-phosphate will continue, but the glycerol 3-phosphate concentrations will begin to rise because we will not be able to go backwards in our dehydrogenase reaction. Elevated concentrations of glycerol 3-phosphate, of course, will give you the backbone structure of triglyceride synthesis. The triglycerides, of course, are packaged into VLDL, and these are sent out into the blood. Now, if we drink substantial amounts of alcohol, ethanol, during a fed state, we are going to push the limits even greater on this metabolic imbalance. What that primarily means is that we are going to be pushing more and more of the substrates into fatty acid synthesis. For example, the lactate that is made by the pyruvate reaction from lactate dehydrogenase to try to regenerate some of the NAD, the lactate can be used by the liver and also by the muscle. If we increase the flow of substrates in a fed state in the liver and push the envelope here into acetyl-CoA production in the cytosol and increase our fatty acids, the packaging step into triglycerides could be inhibited because the pathway is now saturated. Saturated means substantial amounts of fatty acid and triglyceride synthesis, but no place to put them because we have a rate-limiting step on VLDL synthesis. If the triglyceride levels begin to increase in the liver with no place to go, this will lead to alcoholic fatty liver disease. Now let's take a look at ethanol metabolism in the fasting state in the liver. Of course, this is going to be signaled by glucagon signaling. So under these conditions in fasting, of course, we do not have glucose coming in, and glycolysis is going to be inhibited because we are performing gluconeogenesis. The ethanol is still going to be oxidized by alcohol dehydrogenase, generating our NADH. Same reaction that we saw in the fed state to make acetaldehyde. The acetaldehyde will now enter the mitochondria and be processed to acetate. By the acetaldehyde dehydrogenase enzyme, resulting in more NADH, this time in the matrix of the mitochondria. And at this point, the acetate can be used by either the liver or it can be subject to secretion into the blood so that other tissues, like skeletal muscle, will take this up and use it. If the liver uses this, this is going to convert this into acetyl-CoA by acetyl-CoA synthetase. Now, what is also happening in the fasting state in the liver is another pathway to increase the secretion, the synthesis of acetyl-CoA. And this is beta oxidation of fatty acids. In the fasting state, we have glucagon signaling, so the adipose tissue is signaled to release fatty acids. The liver takes up these fatty acids, transports them to the mitochondria, and undergoes oxidative reactions to release acetyl-CoA. So now we have two sources of acetyl-CoA, which is going to dramatically increase the concentration of acetyl-CoA. Increasing acetyl-CoA, of course, is going to take pyruvate and it's going to inhibit the further production of acetyl-CoA by inhibiting the enzyme PDH. pyruvate dehydrogenase. What acetyl-CoA will do is to activate pyruvate carboxylase. And this will convert pyruvate into oxaloacetate. The oxaloacetate, of course, will now be converted to malate by reversal of the malate dehydrogenase enzyme. And now we can take the malate and enter gluconeogenesis to make glucose. Now the problem with this reaction is that we are going to be limited on the substrate pyruvate for this reaction. Recall with ethanol, we have a substantial amount of NADH being made. Our transport shuttle is going to be slowed because the enormous amount of acetyl-CoA that we have in the mitochondria coming from the acetate from ethanol oxidation and the beta oxidation from fatty acids is going to keep the NADH levels very high in the matrix of the mitochondria. And so the NADH levels in the cytosol will build up. What that is going to do is take pyruvate, as we saw in the fed state, and convert this into lactate, which can lead to lactic acidosis. This, of course, is to regenerate our NAD, but notice what we're doing here is we're taking pyruvate out of the gluconeogenic pathway because we are consuming the pyruvate in the reaction to make lactate. So not only are we creating lactic acidosis in this situation, but we are also reducing the amount of glucose being made in a fasting state in the liver, leading to hypoglycemia. Now if we return to the matrix of the mitochondria, under normal conditions we have a substantial amount of acetyl-CoA because of beta oxidation. And recall in the extended fast starvation state, as acetyl-CoA levels rise due to time of oxidation of fatty acids, we will now induce ketone synthesis. Add the additional acetyl-CoA source of being acetate from the ethanol oxidation, and now we have dramatically and more rapidly increased acetyl-CoA concentration in the mitochondrial matrix. So what this is going to do is substantially increase the concentration of ketone synthesis. This will lead to ketoacidosis. Again, another mechanism for dropping the pH in the blood. So these reactions, both in the fed and fasting states, are specifically enhancing the normal metabolic activity of the liver, of the hepatocyte. But now what we were doing is increasing essentially the energy charge by oxidizing ethanol in addition to our normal fuels, being glucose in the fed state or beta oxidation and fatty acids in the fasting state. By adding to the extra energy charge that we normally have, we're essentially overloading the system. And again, like any other biochemical reaction, if we overload the system, we're going to have backups on certain substrates. And these backups can lead to excessive production of normal molecules that eventually become toxic. For example, in the fed state, we are adding to the energy charge by increasing the amount of acetyl-CoA moving into fatty acids. We've seen here that we can increase this acetyl-CoA coming in, and this acetyl-CoA, of course, in the fed state, can be added to the normal acetyl-CoA from acetate and the acetyl-CoA synthetase. This here increases the charge even more than normal, and so it is going to essentially push the production of fatty acids, which is going to saturate, leading to fatty liver. In the fasting state, we already have a normally catabolic state, and here we are adding to this problem by increasing our fuel availability through ethanol, which will increase our charge again in the cytoplasm and increase our substrate flow into the matrix of the mitochondria, which will add even further to the charge that's already being there by the oxidation of fatty acids. This will tip the balance of our normal biochemistry to produce ketones earlier in the fasting state and at a greater level, leading to ketoacidosis. In addition, the charge is going to throw off our pyruvate because we have a high NADH charge in the cytoplasm in a fasting state, which is normally kept very low. But by elevating that, we're taking pyruvate out of the gluconeogenic pathway and pushing it into lactate. One final note is that we're depleting pyruvate in this reaction. In order to create lactic acidosis, we're going to need to keep feeding this pathway. And the question is where does the pyruvate come from? Well, recall we're in a fasting state, and if we're considering alcoholism, where the diet is already poor, we are capitalizing on our amino acids for energy. And the skeletal muscle will be performing lots of transamination reactions by the enzyme ALT, alanine transaminase, generating lots of alanine, which of course is going to go to the liver. The liver picks up the alanine and does another transamination reaction with alanine transaminase to generate pyruvate. So the sources of pyruvate will be coming from extrahepatic sources.